Listen, in aldehydic protons, yes, here also we have pi electron due to the circulation of pi electron in the presence of external magnetic field. Okay, so the pi electrons produce molecular current, and this molecular current, right, induces magnetic field, and the magnetic field, right, the magnetic field actually goes in this way. This is how the magnetic field goes, right? This is the direction of the magnetic field. See, observe carefully. So in the magnetic field, listen, in the middle of the carbon-carbon double bond, a carbon-oxygen double bond, see, the induced magnetic field is opposing the external magnetic field. So this region is called the diamagnetic region. Whereas near proton, the induced magnetic field direction and the external magnetic field direction, they are one and the same. Which means the aldehydic protons experience more magnetic field strength. Therefore, aldehydic protons appear in low field. Not only that, the oxygen is more electronegative, which pulls the electron density from hydrogen through these bonds. So due to electronegativity of oxygen, further reduction of electron density, or reduction of electron density on hydrogen takes place. Therefore, this effect also make the proton to appear in low field. Okay, so aldehydic protons appear in low field. The chemical shift of aldehydic proton is in the range of usually 9 to 10. For some cases it may go beyond 10, but usually the range is 9 to 10 for aldehydic protons. Okay, why? What is the reason? The reason is that the hydrogen, aldehydic hydrogen, right, is present in the paramagnetic region. This is called paramagnetic region. I just put P here. Is in the paramagnetic region, therefore it is de-shielded. The hydrogen is de-shielded. It experiences more field. Therefore, this proton absorbs in the low field region. Low field means large chemical shift. Not only that, the oxygen is more electronegative, which pulls the electron density, right, from hydrogen. Therefore, the hydrogen nucleus or near hydrogen nucleus electron density is very low. This also causes the hydrogen atom to appear in low field. So, due to this combined effect, the aldehydic hydrogen appear in very low field. Therefore, the chemical shift is large. So, chemical shift for aldehydic proton, right, is 9 to 10 in general, 9 to 10. But for some aldehyde, it may go even beyond 10. Okay. In the case of aromatic proton, see, when you place the benzene in the external magnetic field, let me draw here. So this is the direction of the external magnetic field, right? The pi electron starts to circulate. It induces a molecular current, right? This is the circulation of the pi electron. This circulation of pi electron, right, induces what is called a secondary magnetic field. Okay, now listen, let me see here I have shown all the hydrogen. Now, for understanding purpose, I will show just one hydrogen and I will show the effect. Okay, what happens at the hydrogen? See, due to the circulation of pi electrons, it will induce a secondary magnetic field. This is the direction of the secondary magnetic field. Direction of the secondary magnetic field. Okay, see, in the middle of the benzene ring, right, it opposes the external magnetic field. So, middle of the benzene ring, right, is considered as the diamagnetic region. Whereas, near proton, the direction of the magnetic field, the induced magnetic field is exactly parallel, right? It parallel with the external magnetic field. I repeat, due to circulation of, due to the molecular circulation current, molecular circulating current, and external a secondary magnetic field is induced. this secondary magnetic field, okay, it actually reinforces with the external magnetic field because they are in parallel. Therefore, this hydrogen feels more magnetic field, which means this hydrogen absorbs the low field itself. Okay, so the chemical shift of aromatic protons usually appear in the range 6 to 8.5. So chemical shift is somewhat high. What is the reason for the high value of chemical shift for aromatic proton? The reason is that due to pi electron circulation, it is called pi electron anisotropy. Okay, due to pi electron circulation, a secondary magnetic field is induced. That secondary magnetic field, okay, it is paramagnetic, right? It creates a paramagnetic region around this proton. Therefore, aromatic protons appear in low field. Low field means high chemical shift. So, chemical shift for aromatic proton is usually in the range of 6 to 8.5. Okay, right? Keep this in mind. We'll discuss few anilines here and one pyrene compound also. Listen, this compound is called methano 10 aniline, right? Methano, so we have a methylene group here, so it is called methano 10 aniline, and you know very well this molecule is aromatic. This molecule is aromatic. Okay, 10 aniline is not aromatic due to trans hydrogen interaction. It is not aromatic, but methano 10 aniline is aromatic. Okay, and in this compound, the methylene protons has chemical shift of minus 0.51. See, minus 0.51, this value indicates that it is highly shielded. The protons which are present in the middle of the, okay, it is just above the ring, and which is present near the middle of the ring. Okay, it is above but near the middle of the ring. Right? Whereas the chemical shift of the aromatic protons are the protons attached to the ring. Right? Then the 10 aniline ring. Okay. These protons, they show chemical shift 7.29, which is de-shielded protons. Okay. High chemical shift means de-shielded. Low chemical shift means shielded. Simple. Now the reason is that, see, in the presence of external magnetic field, okay, these pi electrons, they are, see, this ring is planar. So this pi electron makes a circulation. So it induces or it produces what is called a molecular circulating current. A current is produced. And this current, listen, induces a secondary magnetic field. This is the direction of the secondary magnetic field. This is the direction of the secondary magnetic field. So if you observe this carefully, listen, near this methylene proton, the induced magnetic field opposes the external magnetic field. Therefore, this region, it is actually a diamagnetic region. Let me write D symbol here. This region is diamagnetic region. Whenever proton is present in diamagnetic region, okay, it is highly shielded. Highly shielded protons, okay, it is more shielded, right, even compared to TMS. So it appears, okay, beyond TMS in the right hand side. Okay, it appears in the high field beyond TMS. That's why the chemical shift value is minus 0.51 ppm. Okay, whereas the protons attached to the aniline ring, these protons, see, these protons are in the paramagnetic region. See, the direction of the secondary magnetic field and the external magnetic field are in the same direction. They both are in the same direction. If both are in the same direction, we call that region as paramagnetic region. If protons present in paramagnetic region, okay, we call those protons as de-shielded protons. De-shielded means the proton will give signal in low field. Low field means high chemical shift. So chemical shift of this aromatic, right, or the aniline protons attached to periphery of the ring, right, shows chemical shift of 7.29, and the protons present the methylene protons which are present just above the ring, okay, which appears at minus 0.51 chemical, right, I field. Okay. This compound is called dimethyl. Here we have a methyl group behind the plane, and this methyl group is towards us. Okay, it is above the plane. This methyl group is below the plane, and this methyl group exists above the plane. Right. Now, when you apply the magnetic field, right, external magnetic field, what will happen? These pi electrons, okay, induces current. It is called molecular circulation current. Right? The molecular circulation current is induced, and this current induces induces a secondary magnetic field. Because of the secondary magnetic field, what will happen? See, because of the secondary magnetic field, the secondary magnetic field goes in this direction. So let me show like this. It goes in this direction, right? So what happens is that near this proton, right, the direction of the secondary magnetic field and the direction of the external magnetic field are same. So we call this region as paramagnetic region. In paramagnetic region, the hydrogen atom, if hydrogen atom is present in the paramagnetic region, they are highly de-shielded. So this hydrogen is de-shielded. Okay. Whereas the methyl group, the hydrogen present in the methyl group, this methyl group, these protons, they is present in the diamagnetic region. This region is called diamagnetic region. Why? Listen, in this region, the direction of the secondary magnetic field, induced secondary magnetic field, is exactly opposite to the external magnetic field. So this region is called diamagnetic region. In diamagnetic region, the methyl protons, right, experiences it is actually shielded. Okay, whenever protons present in diamagnetic region, it is shielded. So the methyl protons are shielded, so it appears in the high field region. Okay, yes, methyl proton, methyl which is present above and the methyl which is present below, both the methyl group are in the shielded region. They are highly shielded, and it appears beyond, see, beyond TMS. Chemical shift is minus 4.2. Whereas the hydrogen which is attached to the periphery of the ring, these hydrogens are present in paramagnetic region, okay, and they are de-shielded, so they appear in low field with the chemical shift of 8.14 parts per million. Okay, take it. So this molecule is called 18-aniline. It has totally 18 carbon. Okay, so if you count, so this is carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So it has 18 carbon, and see, we have conjugated double bonds. Double bond, single bond, double bond, single bond. It is conjugated. Right? Observe carefully. There are, see, 6 hydrogens. See, 6 hydrogens are present inside the ring. Observe carefully. There are 6 hydrogen present inside the ring, and 12 hydrogen. Count the hydrogen. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. 12 hydrogens are present outside. Okay, let me write. See, 6 hydrogens are present inside the ring, and 12 hydrogen are present outside the ring. And all the 6 hydrogen present inside, they are equivalent, and all the 12 hydrogens present outside, they are also equivalent. But the inner hydrogens and the outer hydrogens, okay, they are not same. They are not in the same environment. See what I am trying to say? At low temperature, observe carefully, very, very important. At low temperature, the molecule assumes almost planar structure. Okay, the molecule assumes planar structure at a low temperature. No molecular tumbling takes place, so the molecule is almost planar or planar. If the molecule is planar, then these pi electrons, okay, in the presence of external magnetic field, these pi electrons, okay, induces a molecular current with a large circle, okay, which induces a molecular current with large circle. This current, molecular current, induces a secondary magnetic field. Okay, the secondary magnetic field, observe carefully, the secondary magnetic field goes in the direction such that, so let me show you here, I'll show you here, I'll just show here only, okay. Listen, this is the direction of the external magnetic field, right? Listen, the inside hydrogen, near inside hydrogen, the direction of the external magnetic field and the direction of the direction of the external magnetic field and the direction of the induced field, they are exactly opposite. So inside the ring there is a paramagnetic region. Diamagnetic region. What about outside the ring? Outside the ring, see, outside the ring, the direction of the induced magnetic field and the external magnetic field, they are parallel. Therefore, outside the ring, okay, the region is called paramagnetic region. You know very well, paramagnetic region is called de-shielded region. De-shielded region, and diamagnetic region is called shielded region. Shielded, okay. If protons are present in shielded region, see, the protons which are present inside the ring, they are in the de-shielded region. I am very sorry, they are in the diamagnetic region. Diamagnetic means highly shielded. Shielded means they appear at a high field or low chemical shift. I repeat, due to the circulation of pi electrons, you will get a current, molecular current is set up, and this molecular current induces a secondary magnetic field. The direction of the secondary magnetic field is such that outside the ring, the direction of the external magnetic field and the direction of the direction of the induced field and the direction of the external magnetic field are same. Therefore, outside the ring, the regions are called paramagnetic region. Whereas inside the ring, the direction of the induced magnetic field and the external magnetic field, they are opposite. So inside the ring, the region is called diamagnetic region. Keep this in mind. Protons present in diamagnetic region, okay, they are highly shielded. Shielded protons appear at a high field. So inner protons appear at a high field. See, if you take NMR spectrum at low temperature, okay, inner proton only 6. So I'll get peak with small intensity. Okay, and outer protons, there are 12 hydrogen. So outer protons shows a peak with a high intensity. Okay, the intensity ratio is almost 1:2. This is 1, this is 2. Okay, now the question is, why inner hydrogen appear at a high field? Outer hydrogen appear at low field. Listen, this is very important. Inner hydrogens are present in the diamagnetic region, or if protons present in diamagnetic region, those protons are highly shielded. Whereas outer hydrogens are present in the paramagnetic region. Okay, paramagnetic region, if proton is present in paramagnetic region, they are highly de-shielded. Shielded protons appear at high field. De-shielded protons appear at low field. Low field means high chemical shift. High field means low chemical shift. You know very well. So, the 12 hydrogen which are present in low field, okay, it has high chemical shift. So, this chemical shift 9.3, it corresponds to the outer protons. Outer protons, also called periphery protons. Periphery. Okay. And the chemical shift minus 3.0. See, minus 3.0 means just beyond TMS. Beyond TMS. Okay, minus 3.0 means beyond TMS. So it means it is highly shielded. Okay, so inner protons are highly shielded. They appear at high field. High field means low chemical shift. So this chemical shift corresponds to inner protons. Okay. Now listen carefully. This is very important. So chemical shift for 6 hydrogen. This peak. For this peak, first the peak appear at high field. The peak appear at high field as chemical shift of minus 3.0. Whereas the peak appear at low field as a chemical shift of 9.3 ppm. Okay, listen, we will get two signals, one for inner proton and one for outer proton. Keep this in mind. In the case of aniline, if inner proton appear at a high field and outer proton appear at a low field, then the molecule of the aniline should be aromatic. This is a method of predicting whether an aniline is aromatic or not. Okay, how to do? Very simple. At low temperature, you take NMR for an aniline. If inner protons appear at a high field and outer protons appear at a low field, then the molecule should be aromatic. Now the next question arises. Listen, what happens if I increase the temperature? Say, suppose if I increase the temperature to say 150 or 100 degrees Celsius, right? Or at room temperature, for example. Okay, make 150 Kelvin, right? If you go to high temperature itself, so that will give some clarity. This is low temperature, this is high temperature. At high temperature, what will happen? The planar molecule starts to tumble. Okay, the molecule become non-planar due to tumbling motion. So molecule become non-planar. Therefore, the 6 hydrogen present inside the ring and 12 hydrogen present outside the ring, okay, they starts to mix up. Okay, because of the fast tumbling, right? Fast tumbling. Okay, it is very difficult to distinguish inner hydrogen and outer hydrogen. Therefore, right, all the protons, all the 18 protons, they appear at one particular field or chemical shift. So we get only one signal. So 18 aniline, right, will give one signal at high temperature in the NMR spectrum. At low temperature, they'll give two signals. Okay, one for inner proton, the other for outer proton. If inner proton appear at high field, it should be aromatic. So 18 aniline in which inner proton appear at a high field, therefore 18 aniline is aromatic molecule. Okay, at high temperature, right, molecule undergoes fast tumbling. Because of the fast tumbling, all the 18 hydrogen, okay, becomes equivalent and they give only one signal in the NMR. Right? It's very simple. So the next example is 16 aniline. Listen, see this carbon number 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. Yes, there are 16 carbon and there are 16 hydrogen. Out of 16, 12 hydrogens are present outside the ring and 4 hydrogens are present inside the ring. Okay, let me write here. 4 hydrogen present inside the ring. Inside the ring. And 12 hydrogens are present outside the ring. Observe this carefully, very important. Right. Now, at the low temperature, see, right here, at low temperature, the molecule assumes planar structure. Right? It takes planar structure. Since the structure is planar, these pi electrons, okay, yes, in the presence of external magnetic field, these pi electrons, right, induces or produce molecular circulation current. And that current induces a secondary magnetic field. It induces a secondary magnetic field. right? Observe this carefully, this is very important. The induced current, right, is in this direction. One second. Yeah. So in this molecule, listen, the circulation of pi electron creates a secondary magnetic field, and secondary magnetic field direction, see, observe carefully. Let me draw like this. Secondary direction is such that, listen, outside the ring, the direction of the induced magnetic field, outside the ring, the direction of the induced magnetic field is opposite to the external magnetic field. So this region is called diamagnetic region, right? Diamagnetic region means shielded region, it is highly shielded. Whereas inside the ring, the direction of the external magnetic field, right, and the direction of the induced field and the external magnetic field, they are same. Therefore, inside the ring, okay, there is a paramagnetic region. Paramagnetic region means de-shielded region, de-shielded. Observe carefully, shielded protons appear at a high field. Shielded protons, high field. Okay, so outer hydrogens, there are 12 outer hydrogens, right? They are in the diamagnetic region, so it is highly shielded, so they appear at a high field. Yes, see, 12 hydrogens appear at a high field. Whereas the 4 hydrogens which are present inside the ring, they are in the paramagnetic region. Paramagnetic region means they are highly de-shielded. Since they are de-shielded, these 4 protons appear in low field. The 4 hydrogen appear in low field. Okay, so this is the NMR spectrum of this compound at low temperature. NMR spectrum of 16 aniline at low temperature. Now observe carefully, inner protons appear in low field. In the previous example, inner protons, see in the previous example, inner protons appear at high field, outer proton low field. Whenever inner proton appear at a high field, okay, in an aniline, then that aniline should be aromatic. If inner proton appear at a low field, see, inner proton low field, okay, this implies that 16 aniline is not aromatic, it is actually anti-aromatic. So it is an anti-aromatic molecule. Okay, so the next example is a Nor-Bornein system. Okay, in Nor-Bornein system, see, let me draw the structure of Nor-Bornein so that you get some clarity. Listen, Nor-Bornein. If you are not able to understand the structure given here, just observe this. Okay, this is Nor-Bornein. This is Nor-Bornein, which has, listen, these 2 hydrogens, right? The hydrogen which is in the same side of double bond, right? Or which is close to the double bond, I can say in the other way. It is called syn hydrogen, and the hydrogen which is opposite to the double bond, it is called anti-hydrogen. This hydrogen is called anti-hydrogen. And here I have a CH2 group, here I have CH2 group. This CH2 group, one hydrogen below the ring, the other hydrogen is above the ring. This hydrogen is called endo-hydrogen, and this hydrogen is called exo-hydrogen. Okay, so in this molecule we have different hydrogens, syn, anti, and endo-exo. Similarly, this carbon also has endo-exo. Now, in the presence of external magnetic field, listen, this pi electron will produce what is called circulation current. Because of that current, okay, a secondary magnetic field is induced, right? Observe carefully, this is very important. What is the effect of the secondary magnetic field? Listen, at the syn position and at the endo, syn protons and endo protons, they are in the shielded region, okay, shielded. They are in the shielded region. Due to the circulation of pi electron, a secondary magnetic field is produced. That secondary magnetic field, okay, produce or create shielded region for syn and endo protons. Syn means this proton, endo means this proton. For syn and endo protons, okay, it creates a shielded region. For anti and exoprotons, they are in the de-shielded region. Okay, this pi electrons, right? Pi electron circulation produce secondary magnetic field. That secondary magnetic field makes syn proton and endo protons in the shielded region and antiprotons and exoprotons in the de-shielded region. You all know shielded protons appear at high field. Yes, see here, for this proton, syn proton, field is 1.07. High field means low chemical shift. Whereas antiproton, okay, this is in the de-shielded region. De-shielded means low field means high chemical shift. See the chemical shift value 1.37, whereas this is 1.07. So this is large because it is in the low field. This hydrogen appear in low field and this hydrogen appear in the high field. It is shielded. This hydrogen is shielded and this hydrogen is de-shielded. Okay, due to the circulation of pi electron, this hydrogen is present in the shielded region and this hydrogen, which is opposite to double bond, present in the de-shielded region. Similarly here, endo and exo. Endo hydrogen is present in shielded region. Shielded region means they appear at high, they appear at the low chemical shift, 0.94. Whereas exo hydrogen present in the de-shielded region, right, which appear at a chemical shift of 1.57. Low field means high chemical shift. Okay, is this point clear to all? Hello? Okay, now we'll discuss some examples about sigma electrons anisotropy. See this molecule, this is actually tertiary butyl substituted cyclohexane. It's a cyclohexane molecule where a tertiary butyl group is substituted. And you know very well, since it is a large group, it always occupies equatorial position. Right? This molecule does not, okay, undergo flipping and form the other isomer called the axial isomer. Equatorial tertiary butyl cyclohexane is more stable. So flipping does not occur in this case. So the molecule, I can say this molecule is highly rigid. Here ring flipping is very difficult. So the molecule is rigid. Now, in the presence of external magnetic field, observe carefully. In the presence of external magnetic field, right, what will happen? The sigma electron, see, suppose I will take this sigma electron. This sigma electron, okay, undergoes circulation. It creates circulation current. And because of that current, an external magnetic field, a secondary magnetic field is induced. And this is the direction of the secondary magnetic field. Let me draw like this. Okay. So equatorial hydrogen is in the dash region. Direction of the external magnetic field and the secondary magnetic field are same. So what is this region called?
Paramagnetic.
This is paramagnetic region. What about this region where the external magnetic field?
Diamagnetic.
It's a diamagnetic region, right? Hydrogen, see, equatorial hydrogen is present in equatorial hydrogen is present in paramagnetic region. Therefore,
De-shielded.
it is de-shielded. De-shielded means?
Down-shielded.
De-shielded means high chemical?
Low-shielded.
Yes, see, equatorial proton, observe carefully this line. Equatorial protons always found downfield. Always found downfield. Equatorial protons always found downfield. Okay? Always found downfield. Right? So, equatorial proton, since it is downfield, high chemical shift. So, for the equatorial proton, the chemical shift is 1.62. And for axial proton, the chemical shift is 1.12. What is the difference between these two? What is the difference? 1.62 and 1.12. What is the difference roughly?
0.5.
Yes, yes. Remember, in NMR spectrum, see axial hydrogen and equatorial hydrogen, they differ by roughly 0.5 ppm. If this is 1.62 and this is 1.1, roughly, right? And listen, equatorial hydrogen always found in downfield. Downfield means high chemical shift. So among the two, high chemical shift is for equatorial hydrogen. Low chemical shift is for axial hydrogen. Okay, now listen, see here the second example. Now it is not tertiary butyl substituted cyclohexane, it is substituted with one nitro group also. Okay, let me take this as carbon number 1, this is 2, this is 3, this is 4. So it's called 4 tertiary butyl, okay, nitrocyclohexane. 4 tertiary butyl nitrocyclohexane. 1 nitrocyclohexane, we can say nothing about it. And in this, there are 2 isomers possible. In one isomer, hydrogen is in the axial position. In the other isomer, hydrogen is in the equatorial position. If I keep this molecule, or if I place this molecule in an external magnetic field, and if I pass radio frequency radiation, tell me which hydrogen will appear at low field, equatorial or axial? Is the molecule can undergo flipping? Is flipping is possible here?
No, sir.
Yeah,
No,
due
sir.
to the presence of tertiary butyl group, flipping is difficult. Therefore, the ring is rigid. If the ring behaves like a rigid ring, then equatorial hydrogen always found at downfield. Downfield means equatorial hydrogen downfield.
High chemical shift.
Downfield means high chemical shift. Yes, it gives a value of 4.43. Whereas axial hydrogen, okay, it shows a value of 4.23. 4.23 in the NMR spectrum. So using NMR spectrum, right, if the cyclohexane molecule is rigid, yes, we can differentiate whether the hydrogen is axial or equatorial, right? So now the next example is, I have taken alpha D and beta D glucose. Can we distinguish these two molecules using NMR spectrum? Yes, it is possible. How? Listen, let me draw the structure of alpha D glucose, Haworth projection first. You know very well, in Haworth projection, observe carefully, this is Haworth projection, this is carbon number 1, this is carbon number 2, 3, 4, and this is carbon number 5. In carbon number 1, in the case of alpha D glucose, OH group is below the ring, hydrogen is above the ring. And in second carbon, OH group is below the ring, hydrogen above the ring. Third carbon, OH above, hydrogen below. Fourth carbon, OH below, hydrogen above. In fifth carbon, always CH2OH group is above the ring and hydrogen is below the ring. Always. This is Haworth projection. Now, I'll draw the corresponding chair form. Okay? Chair form. Observe carefully. We draw with the structure so that we get some clarity. Now, this is carbon 1, carbon 2, carbon 3, carbon 4, and carbon 5. Right? Observe carefully. It's very, very easy, but follow this carefully. Now, see, I have a nitrogen here and OH group here. So, what I'm going to do, I'll place OH group in the equatorial position, right? OH group in the equatorial position and hydrogen in the axial position. Okay? Listen, both these OH group on carbon 1 and OH group on carbon 2 are on the same side of the Haworth position. Same side means cis. Okay, so in the chair form, we should place the two OH group on adjacent carbon with the cis structure. Okay, with the cis relation. So, if you place one OH group in equatorial, in the second carbon, if you place the OH group in equatorial, if you place in equatorial, what will happen? You will get trans. If you place in axial, I will get. If you place it in action,
Cis, cis.
we'll get cis, correct? We'll get cis. Now listen carefully, this is very important. So what we do is that we place OH group in the axial position and hydrogen in the equatorial position. Why I am doing this? Because otherwise what will happen? So I'll place hydrogen here and OH group here. I place one OH group at the axial so that remaining OH group comes to equatorial. That's the meaning. Okay, that is why we place OH group in axial. Actually, we should place in normal molecule, in other molecule, we place OH group in equatorial only. But for alpha D glucose, at carbon 1, OH group is placed in axial. Why? If you place OH group in axial, all other OH group comes to equatorial position. See how? In second carbon, okay, since OH on the first carbon and OH on the second carbon are cis geometry, okay, so what I'm going to do, if I place one OH group in axial, the second OH group should be in equatorial, so that they are in the cis position. Right? And 2 and 3 carbon in which OH groups are opposite, they are trans. Okay, trans means, if this OH group is equatorial, then this OH group should be in equatorial, so that both comes to trans position. Then third carbon and fourth carbon, they are trans. See, OH above, OH below, they are trans. So if I place this OH group in equatorial, this should be in equatorial. This OH group should also be in equatorial. Okay. Then what about here? Here always see this OH group and CH2OH, they are trans. Since this is placed in equatorial, this CH2OH should also be placed in equatorial position. CH2OH and hydrogen is here. This is the chair form of alpha D glucose. Right. Similarly, I will draw chair form of beta D glucose. Okay, if we draw the Haworth projection first, so that it is easy for us to draw the structures. Okay, 1, 2, 3, 4, 5, 6. This is carbon number 1. In beta D glucose, OH group in carbon 1 should be above the ring and hydrogen should be below. The next carbon, OH group below, next carbon, OH group above, OH group below, hydrogen above, hydrogen below, here CH2OH above the ring. Now, if I draw the corresponding chair form of this molecule, how the structure looks like. See, here, I'll place in the carbon 1, I'll place OH group in equatorial now and hydrogen in axial. And see, this OH and this OH, they are opposite, they are trans. Therefore, if I place OH in carbon 1 in equatorial, OH2 in carbon 2 should also be in equatorial, so that they are trans. Then second carbon and third carbon OH groups are trans. So if this is equatorial, this should also be equatorial. Okay, hydrogen should be axial. Similarly, here OH group should be equatorial, hydrogen axial. Here CH2OH group should be equatorial, hydrogen should be axial. Right. I think up to this the concept is clear to you, right? Now listen carefully. Listen, when you apply an external magnetic field, right? When we apply an external magnetic field, what will happen? See, in the carbon 1, I am just focusing on carbon 1. In carbon 1, due to sigma electron anisotropy, this equatorial hydrogen always found in downfield. And what is the chemical shift? Let me write. And here, in carbon number 1, the hydrogen is in axial position, so it is present in the upfield. Right? This is always downfield. Axial hydrogen is always upfield. Upfield means low chemical shift. And we get a chemical shift of 4.6 for this hydrogen, and we get a chemical shift of, this is 4.6. So just add roughly 0.5. If I add 0.5, I'll get 5.1 something. So it comes around 5.2 ppm. The difference between axial and the equatorial hydrogens in the rigid systems should differ by 0.5. Listen, among these two isomers,
Students, hydrogen.
beta is more stable.
Alpha.
Beta D-glucose is more stable than alpha. Why? In alpha, one hydrogen is in axial. All the remaining groups are equatorial, comfortable, good. But one OH group in axial. But in beta D-glucose, all the groups, all OH groups and CH2OH, everything is in equatorial. Okay, no 1,3- interaction, no repulsion, nothing. So beta D-glucose is more stable than alpha D-glucose. Keep this in mind, very, very important.